Okay, another problem here. Pick up where we left off before. Let's see. Okay, here it is. Okay, so they want us to here, r equals -3. Now, it says convert, first of all. I want you to see something before we convert it. R equals -3. If you build a table, theta and R, the R, this is your equation, has nothing to do with theta. It's independent from theta. So whatever you do for the theta isn't going to matter. R is still going to be -3. Okay, so I can pick theta to be 0, pi over 4, pi over 2, 3 pi over 4, pi, maybe 3 pi over 2, and maybe I get back all the way back to, well, we can do 7 pi over 4, and then finally 2 pi, let's say we get there. Still have -3s all the way around. So let's say this is 3 out here. Okay, and this is -3, and this is +3 if I'm heading in that direction. In other words, okay, so when theta is 0, I have a ray extended this way, and I stop at 3. But since this is -3, I got to go backwards. So my first point is actually over there. Okay, then at pi over 4, come up this way, but I go backwards 3 units. So I'm here. And then at pi over 2, I'm up here with my ray, but I go backwards along that ray down to that point. And I continue in that fashion, always going backwards along the ray until I reach here, then I'm here, then I'm here, then I'm here, and finally, when I reach 2 pi, I'm back over here again. So I've started off heading around this circle in this way. And it is a circle. Okay, so that's graphing it without the rectangular coordinates. Now let's look at this thing. We already know it's a circle, but if you take this, you square it, you get a 9, but that's x squared plus y squared. And there's your circle with radius 3. Okay, first thing, sketch the graph. You'll have to, here's theta, here's r. So if theta is 0, then r is 0. Right there. If theta is pi over 4, then r is pi over 4. Wow. Okay, so come along this. Now that's pi over 4 is about, what is that, point, well, about 0.77 maybe. That's what, 0.79. Okay. So that's about 0.79. So along this ray, this way, that's the pi over 4 ray, you come out about 0.79. So if this is a 1 along here, then it would be about here. Okay, so right there. Now I missed a whole bunch of angles inside here, but I think we'll be able to see the net effect if I continue on here. Let's go to, let's do pi over 3. Well, that would make this pi over 3, which is about what? 1.04. So at pi over 6, it's right here. It's a little bit bigger. So I'm over here now. And let's jump to pi over 2. Well, that would be pi over 2, which is about 1 point, I think was it 5.9? 1.57, sorry. That's a 7 there. 0.57. And that's about here. And then so you can kind of see the way it's kind of coming outward. As we move out, it gets larger. And by the time you get to pi, it is pi, which is about 3.14, right? So that's over here now. Right there. Stay. And then when we get to 3 pi over 2, then this is 3 pi over 2. So that's about, what is that going to be? 3 pi over 2. About 4.7. 4.7. So that's 1, 2, 3, 4, about here. Okay, right about there. So if you were to connect these now, you would see, whoops, you're seeing like a spiraling effect. Continue outward like this. If I could draw it. Now I only did positive values, but you could also use negative values, in which case what would happen is it would come out this. Oops, I don't want that. It would, instead of coming out the way it did here, it would come out like this. No, like that, yeah, okay. And this point would be over here. 2, 3, yeah, like that. And come down like that. And continue. So you'd have that symmetry there. Now, how do you change that to a rectangular coordinate equation, rectangular coordinates? Well, we know r is equal to the square root of x squared plus y squared. Theta is the arctangent of y over x. So there's one way. I mean, it's not pretty, but that's it. Okay, as you can see, it's not nice. It's not a function. You're not gonna be able to solve it for y, at least. I mean, it looks like it's gonna be really difficult to get the y out of here. So anyway, look how simple it is in polar coordinates. Very simple equation. Rectangular coordinates, not so simple. So okay, here we're just talking about a few pieces of info about slope and tangents and tangent lines. Starting with this r is f of theta. Using these relationships, these two here, and the fact that r equals f of theta, we can set up a parametric form like so that theta becomes the parameter. And we get these two functions here. If you can see that inside there, we got f of theta cosine theta, and y equals f of theta sine theta. So we have just the one parameter to create this curve where r is equal to f of theta. Okay, so now using our results with the derivative for a parametric set of equations for that curve, dy dx is dy d theta over dx d theta, and using these, we can get these results here. Now, one result of this, although it's not the fastest way to find a derivative, it still gives us information about the tangents at the pole, because if f of theta equals 0, or f of alpha, okay, I've used f of theta down here, but f of alpha and f of theta, but if f of theta is 0, in other words, this is gone and this is gone, then, and as long as the derivative is not 0, then this is gone also. And we have that dy d theta is just equal to, or dy dx is just equal to sine of theta or cosine of theta, which is the tangent of theta. So, in other words, all we have is at the pole, we have the change in y over the change in x. It gives us a slope right at the pole. Okay, so that's line here. The line theta equals alpha. Okay, theta equals alpha. So whatever that slope is. Anyway, so what it means is that if we have graphs that look like this, for example, let's say a graph comes in and maybe it looks something like this, for example, then and it crosses here at the pole, we can get those tangents. We look for the place where r of theta or f of theta equals 0, then we'll have actually a tangent right there at that place. Okay, tangent is tangent to that angle right in here. Dy dx is the tangent of theta. So, all right. So anyway, it also gives us a little bit of information. Again, we find our horizontal tangents when dy d theta is 0, and at the same time, dx d theta not 0, and vertical tangents where dx d theta is 0, while at the same time dy d theta is not 0. So that gives us a method for finding those. Okay, we're going to do a problem here. We're going to find the slopes of the tangents to the graph at these points. And here's our equation here. This is f of theta. Okay, so we're going to need dy d theta and dx d theta. So we can get those over here. X is our cosine theta, which means we have this. So we can differentiate the way it sits. We can use a product rule. It'd be 1 minus 2. Sorry, not 1. It'll just be minus 2 cosine theta times a cosine theta. And then plus, well, I guess we can say, I'm running out of room here, so I'll make this minus sine theta times 2 minus 2 sine theta. I could probably clean this up a little. This would be cosine squared theta and plus 2 sine squared theta minus 2 sine theta. Okay, so that reduces a little bit. This will be minus 2 cosine 2 theta minus 2 sine theta. Okay, so I don't know if that's really going to help us much, but all right, then this next one, let's see, dy d theta. Let's see, inside here again, we'll have minus 2 cosine theta, and then times a sine theta, and then plus cosine theta times 2 minus 2 sine theta, which is, let's see, this is minus sine 2 theta here, and this would be plus 2 cosine theta, and then minus 2 sine theta, cosine theta. So I got a couple of those together, so that's a total of minus 2 sine 2 theta. plus 2 cosine theta. Okay, so when we put those together over here, we'll have our minus 2 sine 2 theta plus 2 cosine theta over our dx d theta here is minus 2 cosine 2 theta minus 2 sine theta. Okay, so good enough. Let's get rid of all these 2's and get rid of some of these negatives. Okay, this will just be a sine of 2 theta minus cosine theta over cosine 2 theta plus sine theta. Okay, so that's nice. Now, slopes of the tangents of the graphs at these points. Okay, 2, 0. All right, so I've got everything here in terms of theta, so I'm going to need, in fact, I can do it over here. If I'm going to use x and y, then I need to convert here. I need theta, so theta is arctangent of y over x. So for that first point, we have arctangent of 0 over 2, which is 0, so theta equals 0. So that's one value. 3. Oh, wait a minute. Let's see. Okay, that's my mistake. I mean, it's nothing lost, but this was in rectangular coordinates. Okay. This was already in rectangular coordinates, so that's r theta. So I got lucky and got that 0 anyway, even though that wasn't y and x. But, okay. So let's just jump right in then. Dy dx at theta equals 0 is going to be from this equation here. We've got from the bottom one here. We'll have 0 minus 1 over 1 plus 0 is a negative 1. Okay. So that's the slope there. Now at this point, 7 pi over 6. 7 pi over 6 will become sine of 7 pi over 3 minus cosine 7 pi over 6 over the cosine of 7 pi over 3 plus sine 7 pi over 6. I've got a little bit of work to do there. 7 pi over 3 is the same as pi over 3, which would be, the sine would be over 3 over 2. And the cosine of 7 pi over 6 is way over there. It's a minus negative root 3 over 2. Okay, so that's a negative. And then down here, again, that's going to be a half. And the sine of that 7 pi over 6 is a negative half. All right, so all of that just becomes root 3. Wow, because that's a 1 and that's 2 of those. Okay. Got one more there. Let's get that last one. 3 pi over 2. 3 pi over 2. We're going to have the sine of 3 pi minus cosine of 3 pi over 2. And we got the cosine 3 pi plus the sine 3 pi over 2. So that numerator is a 0. Let's see what's going on in the denominator. That's a negative 1, and that's a negative 1. So we get the 0. Okay, so we got our 3 numbers there. Okay, I was just going over some of my arithmetic here, and I just noticed something in my second calculation here. this, I was using this guy here. And in here, I've got a minus instead of a plus right here. This should be a plus, which actually makes that denominator a 0. Okay, because it's plus a negative, so that's a 0. That makes this guy here undefined. Okay, in a sense, what we saw here is that dx d theta is 0, which means we actually have a vertical tangent there. So that's an oversight on my part. I didn't, that one sign changed everything. Okay, so we got undefined there. It's actually vertical tangent. Okay, so I'm gonna double check that last one, make sure that's okay. And it does look okay. I mean, I got the sign in here. That is correct. I didn't make that mistake a second time, so I got the plus in there. Okay, so now I was going to show you a graph of that. Let's take a second and look at the graph of this guy. Let's see. Let's clear that out. That was 2 minus 2 sine theta. Okay, let's see what this gives us. Okay, I see something in there, but it looks too small. So let's do this. And our windows are way too big, probably. And our theta max is too high. Let's go in here first. Let's check the window. Okay, that's fine. The window's okay. Theta step might be a little too small because it's really going slow. So I'll increase that size, and I'm going to do a zoom standard on this one. Make sure my I'm in radians. Okay, I'm going to do a zoom 7 on this one. Okay, it all just stopped there. I'm more curious if there's more to it, whether or not there would be. So let's fix that window. Let's go a little farther with our theta. Let's make this. We'll double that. Make it 4 pi. See what happens. We got a lot going there. Maybe too much, but it doesn't look like there's anything else happening. And okay, so once you have that, you could make a few, notice a few details here. At 3 power 2, you can see it looks like a horizontal tangent, and we did get a slope equal to 0. Over at, let's see, what was this other one here? At theta equals 0, and at theta equals 7 pi over 6, what did we have? At theta equals 0, the line's over here. The slope was -1. That looks like it could be right. A tangent coming through there with a slope -1. At 7 pi over 6, that's someplace over here. It could be right there where it looks like it goes vertical. Right there. Okay, so it is consistent with what we're seeing on this graph. And as far as the window goes on that graph, it surprised me that I had to go all the way to 12. I mean, to 6 pi to get that graph. That's a little disappointing. Maybe if I went from -2 pi to 2 pi, maybe that would give me something a little better. Yeah, I mean, it didn't have to go that far. Let's see. If this is a 0, what's going to happen? It did go around. What did I have before? Maybe I just had it out to pi. So our window is good enough from 0 to 2 pi. I must have had it at pi the first time I grabbed it. Okay, well, anyway, I just wanted to mention that about the calculator. Okay, first let's find those tangents at the pole. Now, they said that they would occur, the theory tells us, that they would occur where r was equal to 0. That's where the curve is crossing the pole. So that means that 3 theta must be either, well, some odd multiple of pi over 2. Okay, and that's, let's see, there's actually, well, since there are 2 places there, yeah, we know that it's going to happen, odd multiples of pi over 2. So I take that back. That has to be, I can't use this. I need an odd multiple of pi over 2. So let's write that as 2n plus 1 pi over 2. And that means theta is this 2n plus 1 pi over 6. Okay. Okay, I got a little work done here. Just save some time. Okay, so we've got these. This is where we, in here, I'll point this out, what I did. Where are those tangents at? Well, if they occur at these values of theta, 3 theta is the odd multiples of pi over 2. That's where they occur. And that means that theta is 2n plus 1 times pi over 6. Solving for theta. So at various values of n, I generate these numbers. And I also check where's my derivative of f equal to 0. And that turns out to be at these numbers. And pi over 3, where n is just an integer. Okay, 1, 2, 3, negatives also. And we get these numbers in here, and you'll notice that they do not coincide with these, and they never will, because they're just, you can see 0, 1, 2, pi over 3, 3 pi over 3, 4 pi over 3. They're all multiples of pi over 3, and none of these numbers are multiples of pi over 3. These are all multiples of pi over 2. So we don't get the same, we won't get the same numbers there, so there's no danger. Anyway, okay, so what does this have to do with the graph? Well, over here now, I started to do some graphing. I let theta be a few different values. I started small, and I stayed small. I didn't jump around too fast. You never know how fast these things will change, so you can't go too fast. I just let theta be pi over 6, so small change. I probably could put in a few more values in there because this one's changing so fast that this is my first point here. And when theta is 0, r is 4. So I'm all the way out here at 4. By the time I get to pi over 6, I've actually already gone all through here and stopped at the origin or the pole. And that's my tangent to the pole right there. That's this line. Comes in here. Draw that like so. That's my tangent. That's theta equals pi over 6. And the graph just comes, kind of scoots in there, tangent to that pole right at that angle. And then it doesn't take much. By the time I get to pi over 3, I'm back over here swinging back around. So I'm at -4. So remember, if I swing out this way, if to pi over 6, I'll be going opposite. I'll be at -4. That's why I'm over here. And then I'm swinging back around to get to 0. By the time I hit pi over 2, I'm back to the pole. Because remember, that's one of my theta values for a tangent at the pole. So I swing back this way and just graze it, just get in there, and I have a tangent, a vertical tangent, because it is tangent to the pole, and this line here, theta equals pi over 2, tangent to that line. So then I continue. I may have cut it a little close here. And by the time I get to pi over 2, I mean, just from going from here to here with my theta, I will actually swing all the way in here, okay, and come back to 0, like that, okay. So I get r is equal to 0 then at pi over 2, okay. Well, let's see, I take that back. I was at up here, I keep track of it. Pi over 3 was -4. I got to pi over 2, I was at 0. Okay, that was that point. And then when I got to 2 pi over 3, I was coming this way. My value went up to this, up to the 4. That's this point. And then when I got, I left out a lot what's going on in here. But the point is, at some point, in fact, it was at 5 pi over 6 when I scraped through the origin again, through the pole. So that's a point in here. 5 pi over 6 was stuck in here. I missed that one. And in there, I scraped through them and went past the pole again. And then continued until I hit that pi again. In other words, came back this way, and then I bounced backwards here to -4. So that's the whole graph. It's going to continue to do what it just did as every time we go through another pi units. So continue out to 2 pi. We'll just keep twirling around and go back again. So something you can do with the calculator. I'm going to show you this. Let me just, okay, I'm going to show you the details on this. I'm in the parametric or the polar mode, and let's see. I'm going to get rid of that. I want 4 cosine of 3 theta. Okay, and I'm going to go and I'm going to use my window from 0. We saw that the whole thing completed itself in pi units, so we're going to do that. We're going to slow it down a little bit by inserting a 0 in here. Okay, and we're going to show a different style of graph. We're going to show how this thing traces out. In fact, you know what? I'm going to go backward. I'm going to make this 2 pi. Okay. Make that 2. Whoa. 2 times that. Okay. That's 2 pi. Okay. And then let's go back to here. I'm going to change the style of the graph here. Get over here on this side and toggle through by entering. You can see I just want those little circles, little holes, because I want to see what this looks like. Okay, let's take a sample of this graph now. Let's take a look at this. Whoa, I lost Okay, so let's see what this looks like now. Okay, compare that to the graph that we have. Notice that it's tracing out the same portion, same thing that we had. Okay, now that was pi units, almost pi units. So it's coming back around. Now it's going to continue. It's just going to repeat what I just did. This is going on the second pi units out to 2 pi. So anyway, that let's stop that, and that's actually going a little too slow. So let's stop that and change that window. That's okay. Actually, the window's okay. Maybe it was a little too slow. Let's delete that and let's show this one here. Okay, let's do this one now. And notice how it goes back around twice and then stops. Okay, so that was kind of neat to see that. That's probably the coolest thing that happened here today, right there. Okay, one other thing. See these, when you get way out here on these tips, it turns out there's a pretty good generalization that we can use, pretty useful generalization about some of these graphs. It's in the textbook, but anything that has this form, cosine of n theta or sine of n theta, anything that looks like that, these are called Rose curves. And if n is odd, then the Rose curve has n curves and petals. Okay, n petals. If n is even, then it's 2n petals. Now we just had a cosine of 3 theta. So notice we have 3 of these petals. Okay, 1, 2, 3. They're all equally spaced, 120 degrees apart. So if you find one, you can find the other 2 in this case. So that's a nice generalization. If we had n, for instance, if we had the cosine of 4 theta, then we would have seen something that looks more like this. It would have come around like this. Finished like that. Well, finished over here. What about 4 of these petals? Let's see. So you should practice, but you have to find that first petal before you know where the others are. So I knew it was going to be starting over here because when theta is 0, we get a 1 or whatever the a is out here, and then by the time it hits pi over 4, okay, pi over 4, we're at -1. So actually, yeah, that's. I might have to take that back, what that looks like. But there's definitely going to be 4 of those. But we should be more careful about what these where that first petal starts and where it finishes. That could be a topic of another graph problem. Yeah, okay. Okay, here's the problem. I said cosine, so I gotta take that back now because I violated my own condition. 4, that means it's gonna be 8 petals. I only got 4 of them in here. So there's actually another set of them in here like that. And the way it traces itself out, it's gonna be more like this. Starting out here, I come in, sweep this way. Let's see, come around this way, sweep through like that, there, come around again like that, that, finally like that. I think I might have missed one in there. Okay, why don't we just do this? Put this on here, and this back on. Okay, no, it's a little too big. Gotta shrink it. Okay. Let's look at just plain old. We'll keep the 4 out there and make it cosine. Oops. 4 theta. Okay. Oh, there it goes. Okay. I need that. There. Okay, so I missed that last one. Let's make that window a little bit bigger. Or you know what? Let's make the graph a little bit bigger. Make that 4 in there. And that should do it. There it is. Okay, so I don't know if you're keeping track of all that. We'd have to slow it down a little bit. I don't want to go too slow, but let's make this 0, and let's make this, make that a 6. So we'll slow it down a little bit. Okay, there it goes. There it is. And again, you gotta trace that first curve or that first petal, get a hold of that, and then know that you have 8 total that you have to fit in, and they're all equally spaced. So they're all, in this case, 45 degrees apart from each other. 45 degrees. So that helps you to get that graph. And I went a little too fast on this one down here. I missed that pedal at the bottom. I missed that one. So that was going a little too fast there. Okay,